Welcome back. Let's talk about the average rate versus the instantaneous rate of a chemical reaction. So up to this point, what we've been discussing has been the average rate of the chemical reaction over a period of time. So we would say, we take a measurement at time 0, and then we take another measurement at time 10 seconds, and then we look at the difference in the concentration over that whole time period, and that gives us the rate. And while that's not a terrible way of doing it, it's not the most accurate way of doing it either, because what we're really getting there is a linear approximation of a curve. The rate is constantly changing, and so what we're kind of getting is we're getting, in the first, so let's say each of these marks here is 10 seconds. So we're getting a rate for this section, a rate for this section, a rate for this section, a rate for this section. So we're getting a linear rate for the whole 10 seconds, when in fact the rate is changing inside of those 10 seconds as well. And so the larger this interval, the more the rate actually varies from the true instantaneous rate. And so if we want to actually continuously be measuring the to get the instantaneous rate, there's a few different ways that we can do this. But first of all, you'd have to actually be able to measure the rate fairly quickly, and we'll talk about how we measure rates later on. Right now, we're going to focus more on what is the actual math, like what's the calculus that happens here when we're trying to take the plot of continuously measuring the concentration and getting instantaneous rates out of it. So the instantaneous rate is the change in the concentration at any one particular time, which would actually be the slope of one point on the curve. Now, if you have taken calculus before, which I believe a few of you have, you probably recognize the terminology here. If you have a curve, so you have a plot of some kind, and you want to get the slope of that curve at a single point on the curve, this is another way of saying we want to get the first derivative of the function that defines that curve. So for really any kind of plot, so again, if we have some kind of plot that looks like this, there is a function somewhere, there's a mathematical function that, when plotted, either exactly or practically exactly matches the curve. There is some mathematical function that we can make that will match that curve. And to get the instantaneous rate, or again, mathematically speaking, the slope at any one point on that curve, we're going to take the first derivative of that function. And so, graphically, what this would look like is if we take a curve like this one here, so this is the same graph that we saw in the previous video. We have the hydrogen curve here. If we pick a point, like this one, for example, and we get the slope at that particular point. So again, the first derivative here, it's the slope right at that point. And if you're going to do that graphically, you would just draw a line to where it was tangent to the line where it just touches that one point. So even though it kind of looks like it's touching the line at multiple points, mathematically speaking, it's technically only touching at that point right there. And so we just extend that line out for however long we want. It doesn't actually matter how far we extend this. We then measure how much the height of that line changes over that time period. And height, the rise over the run is the way it was taught to me anyway. The height over the width is another way of saying it. But rise over run is the slope. And so that value would be the rate at that instant in the reaction. And so in this particular case, we have the negative 0.28 molar. That is the change. And then the time period over which we were measuring was 40 seconds. And so the rate is 0.007. If we look at the product instead, so if you look at the HI, you can see how the slope is a bit different here. We have, over the same 40 seconds, a difference in 0.56, but we do have to take this 2 into account. And so if we take the 2 into account by dividing by 2, then we end up with the same rate. And this is what we should always see. We should always get the exact same rate, because the rate doesn't change based on what you're looking at. And if it is, then you did something wrong. Okay, so let's look at an example here. So the graph in figure 12.3, which I've pasted in right there, shows the rate of decomposition of hydrogen peroxide over time. Based on these data, the instantaneous rate of decomposition of hydrogen peroxide at 11.1 hours is determined to be 3.2 times 10 to the negative 2 moles per hour. I know they have a weird way of writing that. I don't know why they write it out this way. But moles per liter is molarity, so this would be moles per hour. Alright. What is the instantaneous rate of production of H2O and O2? So they're telling us what the rate is for the consumption of our one reactant, and they're asking us to work out what is the rate of production of the other two. So now notice here they're not asking us to work out what the overall rate of the reaction is. We will essentially find that as we're going, but they are specifically asking what is the rate of production of this and production of this. So to do that, we need to think about what we had in the last video, which is this. This is going to allow us to relate one part of the chemical reaction to another part of the chemical reaction. And so what we're going to do is, because each of these little sections here are all equal to each other, we are going to pick two of these, one reactant and one product, plug in what we know, and that will allow us to solve for the answer. And by the way, the reason why I said one reactant and one product is because remember we have those negative signs there for the reactants and positive for the products. And in our particular example here, we're going to be comparing two products to a reactant. So we're always going to have the reactant on one side and one of the products on the other side. So we are told that the change in concentration of hydrogen peroxide over time is 3.2 times 10 to the negative 2 moles per hour. And that is just the delta H2O2. That's not taking into account the 2 here, so we're going to go ahead and put that in as well. So we have 1/2, 3.2 times 10 to the negative 2. And by the way, you notice here that they have the negative at the beginning there. That is going to cancel out the negative at the beginning here. So that's why I'm not including it there, is because those two are canceling each other out. Okay, so this is then equal to positive 1/2 concentration of H2O over the change in time. Sorry, that's so sloppy. And this is what we're actually trying to find here. We don't actually need to separate this out any further. If we can just find delta H2O over delta T, that is the answer. That is the rate for that particular part of the reaction. And so what this is going to end up doing is if you work out the algebra here, this half here is actually going to cancel out this half here. So if we multiply both sides by 1/2, we'll end up with just delta H2O over delta T is the same as the hydrogen peroxide. Now, a few of you might have, when I found this answer here, thought, well, yeah, look at the balanced chemical equation. For every 2 H2O2s that disappear, you get 2 waters. It's the same coefficient, so whatever happens to one, the exact same thing happens to the other. And you would be correct. That is a much faster and easier way of doing it, but it's not always going to work out that nice. You might have a more complicated reaction where maybe you have 5 of one thing disappearing and you get 3 of something else produced. And maybe you can do that in your head, but I can't. Oops. We still need to do the oxygen. And so that's just going to be the exact same thing. Only we're not going to have this 1/2 here because the oxygen has just 1 as its coefficient. And so 1/2, 3.2 times 10 to the negative 2 is equal to positive, and you don't normally need to write this in there, but I'm going to write it in anyway, 1 over 1, since 1 is the coefficient, times delta O2 for delta T. And so in this case, it is going to give us a different number. We're just going to divide the 3.2 times 10 to the negative 2 by 1/2, which, let's see, that would be 1.65. Don't trust myself to do that in my head. Close. No 5, so it would just be 1.6 times 10 to the negative 2. Yeah, I don't know why I thought I needed a 5 at the end there. Okay, so 1.6 times 10 to the negative 2 molar per hour is our answer, and that is the change in the concentration of O2. Well, ran out of space again. Change in the concentration of O2 over the change in time. And so again, this probably makes sense. You might have even been able to work that out even without doing all the math, just because whatever change happens to the hydrogen peroxide, the same change happens to O2, just cut in half. Because we have 2 hydrogen peroxides being consumed for every 1 oxygen that is produced. So sometimes with these very simple numbers, it's easy enough that you can work it out without actually writing it out, but I wanted to show you what it would look like to write everything out for those examples where it's not so simple, where you're not just dealing with 1s and 2s. Okay, so this is all well and good, but Freddie is wondering, RIP, by the way, Freddie, how useful is all this without a way of measuring the concentration in the middle of a reaction? We mentioned this earlier. We need some way of measuring the concentration essentially continuously as the reaction is occurring. And we actually have a few different ways of doing this. So to measure the reaction, if it's a very slow reaction, first of all, we actually don't need to measure it continuously. I know I'm kind of backtracking a little bit here because I just said that we were going to talk about measuring continuously, but a caveat to this is if we have a very slow reaction, and I'm talking a reaction that takes not just minutes, but hours or perhaps even days, a very, very slow reaction, you obviously don't need to measure the concentration every second, because it's almost never changing. You're going to have the exact same concentration for a very long time, and then you'll get one data point where it's different, and then you're going to have tons and tons and tons of data points that are exactly the same. So for very slow reactions, you don't need to measure it continuously. You can either just set your instrument to measure every hour or whatever, or you could do what's called sampling. You could take little bits of the reaction out of the reaction mixture and then quench it. Quenching is a sciencey term that just essentially describes stopping the reaction. So you put something into the reaction mixture that you just took out, the little bit that you just took out. You put something in it to stop the reaction from happening anymore. And so then at that point you can save a whole bunch of those samples and measure them all later. So you don't have to be taking... it's just more efficient usually if you can have a whole bunch of samples to measure at once instead of just having one sample every day. So there's a few different options there for when you have these really, really slow reactions. And by the way, there are some chemical reactions that literally take years to happen. You don't really hear about those very often, though, just because they're just not useful. Nobody, most of the time anyway, they're not very useful because you can usually find a faster reaction that does the same thing. But there are chemical reactions that take a very, very long time. If, on the other hand, you have a faster reaction, which is what we're going to be considering in this class, we have a few different ways of measuring how quickly the reaction occurs for these as well. So the most common three ways of measuring the concentration as it changes, as the reaction is going, are these three things here. We have polarimetry, we have spectrophotometry, and we have pressure, monitoring the pressure. So polarimetry is very useful, but only for certain chemical reactions. For the chemical reactions that it's usable, it is actually a really, really handy tool because it is far less likely to have things contaminating it, essentially. One of the problems with spectrophotometry is that you're trying to watch for a particular molecule, but there are other molecules that kind of, in a sense, mess up your view. They kind of cloud up the mixture to where it's kind of hard to tell sometimes if you're only looking at the molecule that you want to look at. Polarimetry and molecules that can participate, can be measured by polarimetry, are decently rare. So the chances of you having something contaminating your sample that will mess with your view of those molecules is also decently rare. So for the samples that it works for, polarimetry is very, very useful. It operates by measuring the change in the degree of rotation of plane polarized light caused by one component over time. So you have to have a molecule in your mixture that has a very specific kind of functional group that can rotate plane polarized light. Now, it's not like these are so rare that you'd never come across them, but they're much more rare than molecules that participate in spectrophotometry. Those are very, very common. So, polarimetry, useful, but only in certain situations. Spectrophotometry is by far the most common one, partially because you can use this with almost any molecule, but also because spectrophotometers tend to be the cheaper ways of measuring things. You can get spectrophotometers for relatively cheap compared to other things like polarimetry. Gas pressure sensors are also pretty cheap, but reactions involving gas are not as common. So the way spectrophotometry works is it measures the amount of light of a particular wavelength absorbed by one component over time. Essentially, it measures the color change. So if, for example, you have a chemical reaction that is occurring and the reactants are purple and they are reacting and going away, so that the purple color decreases with time. And so essentially, a spectrometer is just measuring how purple the reaction is. Now, obviously, it doesn't measure just purple. It can measure lots and lots of different colors, and even colors outside of the visible range, depending on the spectrophotometer that you have. But that is essentially what it does. It measures the change in the amount of a certain wavelength of light that it sees over time. And then the last one here, total pressure. This is just useful if you have a reaction that is either producing or consuming gas. And like I said, it's not quite as useful. There are lots of reactions that do produce or consume gases. But most of the time, especially in this class, we are going to be interested in reactions that take place in solution, in water, that are not producing or consuming gases. But if you do have a reaction that's producing or consuming gas, you can just measure, you can seal it up, and you can measure the change in the pressure, and that will tell you how the reaction is proceeding. So just real briefly here, how a spectrophotometer works is you have some light source. It shoots white light into some kind of a wavelength selector. Here it shows a prism. Most of the time it's not a prism, actually, but just to use something that you're familiar with. We have a prism that separates out the different wavelengths of light, and then we have this little wall here that essentially it has a slit in it somewhere, and you can move the prism in different directions to get different colors of light shining through that little slit. And so you pick the wavelength that you want. That light goes shooting into your sample. Some of it gets absorbed. And so the detector, which knows exactly how much light went into the sample, can figure out how much light came through, and it can work out the difference between the two. And that's what you read out on the computer. So it knows how much light went in, it measures how much light came out, and it can tell the difference. Alright, we will call it there for this video. In the next video, we will talk about determining the reaction order, which is something we have not yet talked about. But we'll look at that and learn about first, second, and zero order reactions. So I'll see you in the next video.